Apologies for the delay. It was a live TV interview, as I understand. So it's my pleasure to undertake the completely redundant task of introducing Wei Pen. So I don't think I have anything to say except that his consistent theme in his research has been to improve the precision of measurements by orders of magnitude. And today Wei is going to talk to us about he's going to tell us news from the FRB Universe.
Well, thank you. Actually, I just learned something new in the last hour, which is that there exists this TV station called CGNT. That I don't know who in this room has heard of this TV station before. It says it is the world's largest newscaster, in case you are not aware of it. Now you know who the world's largest newscaster is. So I learned something new. Hard to believe that there could be the world's largest newscaster that probably nobody in this room has ever heard of before. So I don't know whether there is an audience out there that actually watches this news. Some of you, in fact, actually, I think anybody from China will have heard of this. It's Zhongyang Dianshitai, but it's the English channel of the Chinese Central TV. That I didn't know that was the thing. So I guess the timing is that we had an announcement yesterday by Chime, which got some good press coverage, which is part of the reason why there have been inquiries to learn more about what we've learned. I'm supposed to wear this, I guess. And there's one thing that I hope comes across that I felt didn't come across all that clearly in all the press coverage, is that this is data taken in what we call the pre-commissioning. So we're debugging the system, and the best way to debug a system is to just see what happens even as your system is incomplete and even as your system is being assembled and tested. So these are data taken whose primary goal is not actually to collect the data. So the primary goal is to debug and understand your system. And so the statements being this is 13 new fast radio bursts. The number 13 is actually not all that big a number. There are other surveys. ASCAP has found more than that. Several surveys have found more than that. So it's not the raw number of this commissioning phase bursts that is particularly interesting. Of course, there are many more Chime FRBs that have been discovered under regular operations that are not still being processed. It's really the potential of what we're going to learn, what's in stock for us with the Chime telescope. So here's the picture that we had submitted for the cover of Nature. I don't think it actually made it. How many of you have been to Penticton? Oh, excellent. So you're all familiar. I'm sure that Peter has been there probably before any of these telescopes were built. Last millennium.
It's like being in an apocalypse. I'm not joking, you drive up, there's like a button on a speaker so that'll start talking to you, but it's half garbled.
In Penticton?
Yeah.
Oh, I did not know. So let me start in the background. This dish is the John Galt 26-meter radio dish that was built in the 60s. And there's a movie about the first VLBI experiment. There's a little plaque at the bottom of that dish for the achievement of the first VLBI fringes in 1967. That was given an IEEE milestone. And of course, this was done together with the Algonquin telescope, and we use this telescope regularly. It's a favorite of ours that we do VLBI with in the scintillometry group that many of you are familiar with as well. And in front of it, we've been building the Chime telescope. It's an array of four cylinders. Thank you. That is It's actually a very old idea of building telescopes. For any of you who've heard of the third Cambridge survey, there are many radio objects starting with a 3C. The Cambridge telescope was also a cylinder that was built in the probably 50s. So it's not, that idea is not new. What is new is that in the old days, in the 50s and 60s, when these telescopes were fairly popular, there are actually quite a number of them. In fact, many of the world's biggest telescopes are of this design, including Molonglo's 3C was a big telescope. Bologna has a big cylinder. Russia has a big one in Puccino, and they're all amongst the world's biggest telescopes, but you don't hear much about them. They were, in the good old days, what they did is it was cheap, it was mechanically cheap to build something which is flat physically along one axis. It's easier to shape that. You only make it straight on one axis, curve it the other. It's much cheaper than making it curved in 2 dimensions. Also, you don't need to move things. You can focus in one direction electronically or in software, and in the other direction you can let the Earth turn. That comes for free. So using 2 free mechanisms, and you can have an object, a non-moving object, see the whole sky and still form images in focus. That was certainly the original motivation why people built cylinder telescopes. It's a very cheap way of having a large collecting area, which is why many of them are large. So the name CHIME is a Canadian Hydrogen Intensity Mapping Experiment. It's an initiative that we started to map the universe for the distance distribution of neutral hydrogen. The goal being to map the dark energy, the evolution of dark energy using baryon acoustic oscillations. That's of course a totally different story altogether that I can go on forever about. It turns out that the demands for a 21 centimeter survey is to just see as much sky as you can, as deep as you can. And surveying the whole sky, you don't need to point your telescope. You can use this mechanism that the Earth turns, the transit telescope. The sky will go by sooner or later. And the main novelty really compared to the telescopes built 60 years ago is that instead of phasing only one point on the sky, we phase up all points on the sky. Okay, so this is the ultimate in fast survey speed, because you can point everywhere at once, at least if you have a software beamformer. And the convenient structure here is that the feeds being in a straight line, this is a FFT. So this is the first production fast Fourier transform telescope.
I thought that people didn't do that anymore in the end.
Sorry?
I thought that in the end they didn't do the fast Fourier transform anymore.
Well, that's a long story. For cosmology, it's not our default mode. However, the fast radio bursts are all found in the fast Fourier transform mode. So this is the fast radio burst. For fast radio burst, it's a pure FFT telescope that forms every one of these beams, and that's a fast process. I think what Martin alludes to is we're also doing the expensive n-squared beamforming anyways. So we have a huge computer in there. Just goes to show how cheap computers are these days, that even doing it the slow way, you can form all the beams at once. And therefore, this can be made much, much bigger. That's actually what I was going to get to at the end of the story, that this is just that the news release today is really definitely only the beginning of the CHIME discovery space. And CHIME itself is clearly only the beginning of what one could do on a much grander scale. Since there's no limit to how far you can scale it, there's no n-squared bottleneck in this process. And this has been a very successful collaboration between a number of Canadian institutions, UBC, McGill, Toronto, the DRAO, and we've had a lot of connections through CITA that really seeded this in the early days and continues to connect people together. So today, obviously, I'll give you a little bit of what I think the CHIME results mean. By the way, this is a CITA seminar. It's going to be, you're going to be hearing about it from a theorist perspective. So there'll be almost nothing technical about the telescope itself beyond what I have just said. But a lot of it will be my take on what I think we have learned and where this is taking us. So yes, I'm going to go to that very shortly. But why? This is CITA after all. What the challenges are to theory as a whole. Some basic questions, what we think they might be. What I actually think is probably even more interesting is what they are good for. Okay, in some sense, what they are, I think, is a bit of a detail. The fact that they are coherent radiation, it's like saying lasers. Okay, this laser pointer, why do things laze? Well, it's going to have a very nice physics problem as to why lasers exist, but the users are probably even more interesting than the physics of why they laze. And you can think of FRBs as lasers. They're coherent radiation, and coherent, just like lasers, are different from sunlight by their coherency. So this is an important thing that I think. It's the only known coherent source that is extragalactic. So that's our probe of the universe. I'm going to I'm not going to debate the details of why these things have 20 orders of magnitude higher brightness temperatures than lasers do. So this is, I think, a different game. They are coherent, yes. And where we might see this going. I have to be careful of how I describe coherency here. So the short history, I guess what's it now, 12 years of FRBs, which is, to me at least, a good thing about the field, that it's relatively new, and in fact it wasn't really until 2013 that anybody but the authors of the first paper ever thought this was real. It was suspected to be interference or microwave ovens or other things. That this field is so new that it's really 2013 when anybody started taking it seriously, meaning that there's no entrenched community of this. For example, in many other aspects of astrophysics, there's this school or that school, or if you look into the field of why supernovas explode, well, they've been known about for centuries, and people have been building up their camps over generations, and either you come up to one of these camps or you're an outsider. Here, everybody's an outsider. So it's a good thing to, it's a more, what I would call an equal, a more democratic system where there is something for everyone, for newcomers. Then, so yes, 2013, there was a confirmation, and it's this, we'll hear more about the scattering later on as to what that tells us. Obviously, this is going to be a very biased talk. I think the next interesting step, in fact, Wikipedia agrees with it, which I did not write, that article on FRBs, is that the GVT FRBs that we discovered in another 21 centimeter survey from Green Bank was the first to measure a rotation measure and to demonstrate the effects of two-screen plasma lensing that I'll describe a bit more later. I think unambiguously a very big piece of news was a repeating FRB. That's FRB 121102 repeated. That was announced in 2016. Okay, so this is all, especially the fact that they repeat, at least one of them repeats, is certainly completely changes the number of questions you have to answer. Until then, if it only goes off once, there's almost no limit to things that catalytic things that happen only once. To have it happen over and over clearly substantially restricts your ideas. And in some senses, I think it's a bit of a detail whether or not all FRBs repeat, because there is one that's known to repeat that has all the challenges of FRBs, of energetics, of timescale, all these things are shared by it, and it repeats. So you better explain this one for sure. And once you've explained that one, whether it explains all of them is, I think a bit of a detail. This is the hard one, and there's more data. We know much more about it, and it has all the challenges. So that's the one I think you want to try to understand. It has at least to the authors of that discovery, a surprisingly high rotation measure. Not surprising to some of us at CITA, like Chris, of course, has been predicting this before these guys discovered it. And until yesterday, there were about 50 published FRBs in the literature. Here is the basic phenomenon of a dispersed pulse, so what you actually see. So again, this is the one that Shoshen, is he here? Yeah, Shoshen discovered this object from our 21 centimeter survey data. And what we see is a pulse that lasts about a millisecond and arrives later at lower frequencies. That's called this dispersion sweep. And it's a lambda squared sweep that shows modulation in intensity. That's scintillation by our galaxy. So this is that's the basic property that's generic to all FRBs. So FRBs are defined as objects that last a short amount of time, typically a millisecond. Sometimes the shortest known are a few tenths of microseconds, and the longest is actually poorly known because they're hard to detect if they last a long time, but certainly we have examples of 100 milliseconds, let's say, is kind of the limit where it's hard to find them, doesn't mean they don't exist. And as they scintillate, modulate, and that's the basic phenomenon. And the dispersion measure is larger than what could be attributed to any line of sight in our galaxy. That's what is characterizes them as extragalactic. For the repeater, of course, we actually know the redshift. It's a redshift 0.2 or so. It's at a gigaparsec distance. It's a good ways away. So
Any line of sight except an arc second for inside the star.
well, okay, if you want to be, again, I have to be careful in this audience of what I say about dispersion measures. There are plenty of lines of sight in our galaxies that have DMs of 1,000. If you happen to pass through an H2 region, there are such, even not galactic center, there are other areas, and that's going to be part of the story as to what areas in the universe could lead to high dispersion measure, either in our galaxy or wherever the FRB is. And indeed, even in our galaxy, there are plenty of places that have DMs of, a galactic center has a DM of 2,000. If you go all the way to the other end, it's probably 4,000 if you went through the whole galaxy. My guess is if it's one arc second from such a star, if you were to look at the FRB right behind it, it would have 2,000 plus whatever is behind it. The RM is known to be 10 to the 5. We get to that. This is all part of the upcoming story. So here is paper 1 from yesterday, or at least the one picture from paper 1 that I think summarizes what's new. So this is this fast radio burst that's dispersed but de-dispersed. So you shift the frequencies by lambda squared, fit for some dispersion measure, in this case 169, and line it all up. And you get a little blip, and it's a very narrow blip. Okay, it's about a millisecond in duration, almost unresolved. And the notable feature that was unexpected is that the chime operates at low frequencies, down to 400 megahertz, is that this burst is very bright and keeps brightening towards the bottom of the band. This has been, until this paper, there was a broad feeling that because all of them have been discovered at high frequencies and none at low frequencies, despite searches, that they either just don't emit or that they are scattered. So here, the second one is an example of the reason why you wouldn't see it. If you take, so many of the fast radio bursts, even at high frequency, are observed to be smeared. They have a fast rise and a slow decay. This is also observed in many pulsars that pass through a lot of material, like the Crab pulsar that passes through its nebula. It also has this type of scattering. And this scattering is a strong function of frequency. At low frequencies, you have a huge amount of scattering. And that smears it out, makes it just harder to detect because you're diluting the flux over a large amount of time, and you're also making the time scale hard to distinguish against other man-made or celestial, or mostly man-made effects here. And because it goes as a force power of frequency, and all the detections were at 3 times higher frequency, it was thought that, well, 3 to the 4th is 100, so that they would all be smeared much more than this. And there probably are many that are smeared much more than this that we just don't detect easily.
You have a really wide band there, so how accurately are you constraining the lambda to the port?
For the top one?
Well,
For the
all of your bursts, when you see the scattering, the positive.
With the scattering, of course, it's harder to know your dispersion measure very precisely. So we have a range. So obviously, when you want something like this, it's a sharply peak visible over the whole band to get a reasonable fit. Even down here, you could see if I were to tilt it one way or the other, clearly because it broadens, this isn't nearly as constrained as that. And you want a narrow burst. So the current mode, we have a 1 millisecond time resolution. If something is shorter than a millisecond, it doesn't help us. But again, these are all work in progress that we will soon be able to have higher time resolution. And then there's no limit. If you have a microsecond burst, well, you can know this DM to another factor of 1,000 better.
In the papers published, you didn't actually constrain the index of the scattering with the frequency index of the scattering.
You mean this index? The scattering or the dispersion measure?
No, it's the dispersion measure, the scattering.
The scattering, we did not float the exponent, no. It was kept fixed at frequency to the fourth power. And I can say that by eye, it looks consistent with frequency force, but there wasn't a formal attempt to quantify that. Here is the second paper from yesterday, which is, again, we heard about this at the FRB day in November, and that was announced on the last day, I believe, that CHIME found another repeating fast radio burst. And here, so there are 5 bursts shown here. And the thing that, I mean, it shares a lot of similarities with the previous known repeater. This one is detected at much lower frequencies and exacerbate whatever problems you already thought you had. So to note is that this is visible at any given time in a small frequency range. Okay, this is a few, maybe 10% frequency width is the instantaneous, so it's peaked in frequency. That's unexpected. If you have normally pulsars or anything which things are moving really fast, highly relativistic, usually whatever you think you're doing is smearing it out over a wide range of Doppler shifts. So it's not entirely obvious how you get a narrow feature if you have something moving very rapidly. And yet it's very bright, so how can it be not moving rapidly? So these are the basic features that one has to try and understand. The other feature you see is that you have a temporal structure that is both frequency and time dependent. Okay, so both the frequency factor changes with time. So not only do you have, for example, we heard last month that maybe it's just a maser or a what they call it. He's got a word for it. Super radiance. Thank you. Super radiance. But those are all lines. Fine, you know, maybe some line that's mirrored. But then why would the line be smeared at a different Doppler frequency a few milliseconds later? Okay, that's a hard one to explain. So this shift, and that's also observed for the first repeater, is a non-trivial thing to try to understand by any physical mechanism, how you can make this happen.
Which would lead to time offset as a function of frequency.
Time varying DM.
That's a millisecond.
Yeah, so the DM is fixed such that each one of these lines is straight.
Changes from one burst to another. So
You mean a millisecond later, you've got a different DM.
no, that entire burst has a different DM than the previous one.
You mean it just tilts the whole thing?
On a common DM, but if they don't all have the same DM, would that lead to the time should be the same?
Okay, so here there are only 5. For the repeater 1, I guess, it has more data. There are over 100 repeating events. And if you look at them, the DM is consistent with not changing at all to less than a part in 1,000 across years. And the feature is always similar, meaning unless you're going to claim that they're going to change by a factor of 20% in a millisecond and then go back again, that's what you'd need, which is equally, you know, that's basically the challenge.
I'm just not sure why it has to be a change during that millisecond.
And so what else?
One burst to another.
So you want to tilt this thing by some amount such that these run on a diagonal, but then you have to explain why it runs on a diagonal. I think you're not changing the physical challenge of why there is frequency time structure. Okay, so I think you still have to, and I'll get to that. I'll give you another example of that in a minute as to what this is, what options you really have. I mean, yes, you can tilt it, but you still have coherent frequency and time structure. That's still the challenge. So one thing the way I like to summarize it is, what have you learned? We have learned that uncommon repetition is common. What does it mean by that? CHIME is very unique that it sees the same sky every single day. whether you want to or not. You have no choice. All the other surveys done before, well, you search, and you find an FRB, and maybe the next day or the next year or the next decade, you go back and stare that place down for a day or how much patience you have, and you see it to not repeat. For chime, every single burst, you will follow up every single day after that. Okay? So the coverage of repetition is orders of magnitude more comprehensive. If you say how many FRB follow-up hours has chime done, well, that's a huge number. Okay, it just takes the number of objects times the number of hours in a year. That's a large number. There's an order of magnitude more than any other survey could even imagine mustering up of following up, unless you only stare at one part of the sky forever and never switch another part of the sky. That's what chime does effectively. And yet we found one repetition after a long amount of exposure. Okay, it says that these repetitions are very hard to find. They're very uncommon. I mean, the repetition is uncommon, even for things that do repeat. They repeat very, very sporadically. So, and that's what I mean by this, right? It's common for things to repeat very, very sporadically, meaning you immediately would say, well, this completely opens up the thought that, well, they all repeat, and some perhaps even more sporadic. You don't have to be much more sporadic for you to just see it, in a year's time. So this concept of there being multiple classes, I think, is now weakened. And plus, as I mentioned, as I started off with, you still have, whatever you think the other class is, this is a class that is hardest to explain. So I've got to work at that first. And once you've explained that, the rest seems like an easy one to deal with. And as I said, the fact that we see plenty of bright events at low frequencies was previously unexpected, and also a self-fulfilling prophecy. So if you look at the low far bounds at low frequencies, they just decided never to search at these dispersion measures that we now know objects exist in. So if they go back and search, they might actually have seen them. But because they were told that it's a waste of time to search, they will be scattering smeared, they just didn't. Okay, so they're misinformed, misguided by theorists. So as theorists, don't misguide all the observers, tell them to look. That's what I tell everybody to look, and we find. That's why, Xiu Shen, I think, he may have felt I sent him on a wild goose chase, looking for, 10,000 candidates and spending a month looking at boring objects, but it paid off. Okay, so don't take, I'm sure anybody who knows me knows that, don't take no as an answer. So I'm going to address one of my favorite phenomena in fast radio bursts. As I said, what they are is only a little bit interesting. I think much more interesting is what they tell us about the rest of the universe. So, as I showed you in our set image from the Green Bank burst that Xiu Shen discovered, there is a small frequency structure in there, and a few things to note. Small scale frequency structure, that's what we observe in the repeater. Okay, small scale frequency, lensing is a generic way which modulates your intensity with frequency. It turns out that of all radio sources known, I'm going to use the word to-first approximation, only pulsars before FRBs, but no scintillates. 1105-23, Xiu Shen's bursts, is the first fast radio burst for which we looked for and found the scintillation. And all the other ones, people just didn't really look, or it wasn't really something that wasn't on people's minds. And here we discovered that this also scintillates. Now, the common lesson that we give in what do you call it, public outreach, is that stars twinkle and planets don't. Okay, so the scintillation is a twinkling effect, and you have to be smaller than the resolution of your scintillating lens to twinkle. So stars satisfy that, and generally planets don't. Of course, it depends a bit on the conditions of the night and the planet. This is not a perfect. I find that whenever I try to do this out at night with friends, it doesn't always work. But at least the idea is there. And in the radio, it is true that except until FRBs, nothing scintillated except for pulsars, telling you that pulsars are the highest brightness temperature objects known in the universe. And for example, masers don't scintillate, and there's no maser known to scintillate, in that sense coherent. So coherent to plasma propagation, that this gives you access to information of a microarc second. Okay, only things that are smaller than a microarc second will scintillate in our galaxy. And there's, other than pulsars and FRBs and perhaps one gamma ray burst afterglow, if somebody catches me on exceptions to this statement, nothing scintillates because nothing has the surface brightness. It also tells you that, when we see AGNs, they're really bright. They're not very bright compared to pulsars. Okay, so brightness temperature of pulsars can be 10 to the 37 Kelvin. There's no AGN anywhere close to that. So these are coherent, intense. In fact, to call them a temperature is kind of silly. This is coherent. It's like TV port, an FM radio station can be 10 to the 20 Kelvin, but that's kind of and there's nothing. The CN tower isn't burning down because of that. It's not a good description of a coherent radiation source. Chris was asking about lambda to the fourth dependent on scattering. I'm afraid I don't have a particular error bar to give on that. Shoshana, did we measure this exponent for 11 or 523? I think we may have. I don't remember. And yeah, there's some errors. There's some allowed region where 4 is definitely allowed. I always think of the force power as a kind of a generic property of plasmas whose dispersion relation goes as wavelength squared, meaning your bending angle is wavelength squared. Your time delay is bending angle squared, so force power is what I would have thought. If you can have a plasma and it goes as lambda squared, that's a very generic expectation that doesn't tell you much other than that there's a plasma involved. However, the fact that the scattering was modulated by the galaxy scintillation actually tells you that the thing even after scattering is less than a microarc second in size. So it tells you that that the majority of papers that are written on intergalactic scatterers are just wasting your time. Okay, that's already been ruled out by data, not by whether or not I believe in turbulence in the IGM. That's a bit of a detail. It's somebody proposing that before there were telescopes that there are objects that are an arc minute in size in the sky. You can say, well, they're not because these things are known to twinkle. So these are generic things that we know, and clearly not everybody has completely absorbed this constraint of plasma lensing that you immediately know things on a microarc second scale. How else do you get to know about a microarc second in astronomy? And since there is lensing, since we now know that there's plasma lensing happening near the fast radio burst, this plasma could be used as a telescope, or as a microscope in this case, to study the burst itself, perhaps with kilometer precision to get very small scale information access. And when I say, what I think is interesting here is this coherence, not so much as a physical process of occupation number, but just the practical coherence that passing through a multi-slit that you form an interference pattern. So, as an example, gravitational lenses, there are dozens known, and where you see multiple images of the same source behind a lens. There's been no example of two sources behind a gravitational lens that forms an interference pattern. They do not interfere with each other. They're too big. They're not, in that sense, not coherent enough for this lensing process. Same even with microlensing. There's been no microlens for which, even though the splitting angle is small and the time delay is very small, microseconds, there's been no occasion where these two form an interference pattern, which tells you a lot more information about the lens when it's interferometric. And that FRBs do that. The fact that they scintillate tell you the multiple paths are coherent and interfering. Okay? So that's a regime. That's why I like to think these are lasers. These are like lasers out at the edge of the universe. Well, it's going to be the edge, gigaparsecs away. Okay? And this allows you to ask questions about things there, things in between, and things in our galaxy. You couldn't ask those questions before. I found it amusing when I first read this book by Schneider, Ehlers, Falco, Gravitational Lensing, a classic textbook on lensing. They have a chapter on wave optics lensing. And they conclude the chapter saying this will never be observed. Unthinkable. That's like Einstein when he calculated the first microlensing effect. He also said, this is how microlensing works. Don't bother looking, it'll never be observed. Of course, it has been observed. And similarly, but it's just because it's such a problem that's so natural to ask and carries a lot of very clean mathematical and physical concepts that they even dedicate a whole chapter of a book to it, even the authors believing it'll never be measured. They think it's so interesting that it should be written about. And that gives you a feeling as to why we're now opening up a domain that is completely known to be interesting if you had a coherent source. We just never had these sources. Okay? But the interestingness has been known for decades, even if never realized. Back to lensing, another paper that Robert, who just moved to Bonn, looks like I ran out of battery here, had a discovery, another Nature paper earlier this year, where this is the magnified pulsars of the black widow 1957 plus 20 observed with Arecibo, again at low frequencies, even lower than the chime events. And these are objects that are magnified. I believe this axis is the brightness relative to the average brightness of radio pulses. So this is a system of a pulsar who has a brown dwarf, with a brown dwarf in orbit, and the brown dwarf is blowing a wind, and the wind eclipses the pulsar for an hour every 10 hours, roughly. At egress, there is an excess of bright pulses, and that's been known before, but this is the first time where we systematically studied these. And you can see, when you're highly magnified, let's say a factor of 20, you're only magnified over a narrow frequency range. And that's because plasma lensing is chromatic. Okay? You can be in focus. To be highly magnified, you've got to be at the focal point of a lens. But the focal point changes with frequency. You cannot be in focus at all frequencies at all times. That's not possible for a plasma lens. And the more highly you're magnified, the more narrow a band you can possibly be in focus for. That's kind of obvious. And here we indeed see that at high magnifications, you see narrow spectral structure. And you see the spectral structure that indeed modulates in time and frequency. And indeed, it can run at an angle intrinsically or in subsequent time periods. Okay, so here we have a observed example of plasma lensing where there is a propagation-induced frequency and time structure that is very complex, and that is currently very poorly understood because, of course, the authors of these books all gave up on this topic because they thought this would never be observed. So I think this is, again, just from the theoretical concept, means, there's a lot of interesting computations and calculations to actually understand these data. This is not a unlikely, but it's a real phenomenon. Good. Now, after having gone on for about my favorite pet topic of lensing, let me continue on things that I think are likely to happen as well. The baryon content, we heard about that from Matt McQuinn last month, so I'm not going to go into that. The plasma lensing I already said way too much about. One-dimensionless number, just to tell you what you're measuring, you're seeing the interference pattern between two lines of sight split by a plasma lens. So two light beams go apart, come together, and they merge again after a gigaparsec, and they're coherent to a nanosecond in order to have an interference pattern. Divide these two numbers, that's 10 to the minus 27, is the equalness of path lengths of two paths each of a gigaparsec. This ratio is 10 to the minus 27, which is much more accurate than LIGO or any other measurement of anything, okay, of any dimensionless strain ratio. So it's a new number that makes you think, maybe we should think about what with a new, whenever you've got less than 5 orders of magnitude of better measurement, it's probably worthwhile thinking, what can you do with a 5 orders of magnitude better measurement? Are there things you can constrain, detect, measure? This is completely a new dimensional space. And again, for this question, it doesn't matter what they are. They're known to exhibit this property. So I think they're going to be exciting no matter what. Okay, I think this is already so observational and so detailed. I'm going to skip over observational issues here. And I'm going to touch a bit upon speculations in the theory world, right? What could these be? I think there's one object that's known to exist, that is known to emit radio waves, of which we don't know why they emit radio waves, are pulsars. And given that there's one thing that we don't understand, why not make the other thing we don't understand the same thing? That's an easy step to take. Why not? And again, there are many different kinds of neutron stars. Magnets are popular because they have a lot of energy. I'm not sure there's anything else behind it. And of course, another popular thing thrown around, if you just read these hundreds of papers that are out there, are black holes. I think, of course, whatever you're going to do with a black hole, it's got to repeat, and because at least two of them are known to repeat. So the challenge is explain the repeaters. Once you've done that, maybe it explains all of them, and if it doesn't, then we'll think again. Now, I do have to point out that the person who invented magnetars, Chris at the back of the room, actually is not a proponent of the magnetar explanation. So I think don't keep telling Chris magnetars. He'll be unhappy if you keep telling him that FRBs are magnetars, despite this being his creation, the magnetars I mean. But another example of how we can get electric pulses is by, again, Chris, I'm sure will be happy to explain in much more detail by annihilating, for example, dark matter near black holes. Here's a completely different example of mechanism. And it turns out there aren't very many other games in town. Okay, you want to make it repeat and have high intensity and not be a neutron star. Okay, even though there are many, many papers, almost none of them are allowed because almost none of them can possibly repeat. So this is, just to have a non-neutron star, there isn't much that can fit the bill these days. Of course, I can go on forever about my own speculation. These are speculations. There's no proof of any of these. But anyways, I skipped over one of the tension issues of why people debate of whether FRBs are relatively nearby, meaning that cosmological evolution is important or not. For example, gamma ray bursts. They are typically very far away, and basically they're very bright. You see the first approximation, you see every one of them, and they're all at the edge of the universe. Okay, because otherwise, the universe has a finite size, so that's what holds the gamma ray bursts, and to some extent for quasars, they also tend to be at the edge of the universe. Other things are, of course, very nearby. There are plenty of examples of things that are nearby, whose distribution then has to be Euclidean, that the number of faint objects must go as the flux to the minus 1.1st power. That's, the volume, the Olbers increase in volume and distance. There are also, I don't think it's controversial to say that at least some FRBs live in very special environments. This rotation measure, I think Chris was pointing out to that the rotation measure of 100,000 is very high. It's the second highest known in the universe. I personally think it may be because people haven't looked in that range as much. You should ask Xian every morning. I've been bugging him to record that data for the last 3 months now. If you ask him every morning, I think we'll motivate him to actually record the data and answer your question. It's yes, I wished, but yes, keep bothering, keep bothering him. Yes, indeed. I'd love to know the answer. Sadly, I don't. Sadly, we don't know yet. And they share a lot of features. They have high RM, they have a high local DM, and they have a temporarily randomly varying rotation measure, first approximation, and large and variable, but not constant, not in a constant way. So I've never heard anybody else agree with my statement, and I don't think anybody disagrees with this statement, but everybody says it's a coincidence. Okay, I'm the only one who thinks this could be interesting.
So far, published with repeater, there are 2 points.
3 points, and they're not in a straight line.
And they hit a straight line.
No, not straight line.
They don't hit a
Yeah, and that's what I mean by non-steady. They're not on a straight line. Based on 3 points. It's not. This is But again, Shoshen is going to get us many more points soon. So again, in the case of the magnetar, it's special in many ways. It's near a black hole. It's young, so it had a supernova. It itself was formed probably in a supernova not very long ago. Of course, then we just had H2 regions that can also lead to a special environment. And this satisfies all of these. In the galactic center, all of these are true. So it's hard to even say that it's one or the other, or all of them combined. Everything is true for it. Going forward, again, I keep stressing, this is the beginning, okay? We're guaranteed to have a lot more coming down. So this is the time to start thinking. It's a new field. We learn so much more. Now is the time to think about what we're going to get out of the existing surveys and what surveys to think about in the future. So there is a sort of, at that time, you can build something bigger. It's just a matter of interest and, I guess, money. But only modest amount of money. So remember that the cylinder is only a tiny fraction, well, 10% fraction maybe of the chime cost is the reflector itself. You can build something 10 times bigger for twice the money, in collecting area at least. And then there is the stage 2 proposal for 21 centimeters that can also, of course, do FRBs. And of course, then there are all the interesting theory questions that I think we'll learn more about. Okay. Here's my last slide, actually. I don't know why it takes me so long to go through 13 slides, but here we are. Certainly, I think FRBs are clearly, an exciting thing to be thinking about. What I encourage everyone to think about is, what are they good for? What would you do with 100 FRBs, with 1,000, with 1,000,000? Then I want to end with one caveat that, many people come to me, and I think people get very distressed that there are papers out there that are just wrong. Well, welcome to life. We know that, in fact, I can assure you that the vast majority of certainly theory papers must be wrong because they're incompatible with each other. And so, you have to live, don't take papers too seriously in this field, or in any other field, but especially in this field. And, think hard of what it takes, what data is robust, what inferences are robust. And this is a kind of, what you call it, almost an alternate truth situation in astronomy, that people are trying to sell you stories that are clearly wrong. Sadly, it happens in other parts of in more important parts of our society as well. But it's an intellectual, thing. It's worthwhile sitting down and, coming to discussions and just analyzing. Is that logic sound, or is it just circular? You wouldn't believe how many circular logic papers are out there that make an assumption and prove their own assumption. So I think it's, anyways, it's an interesting field, interesting time. And I'm always happy to talk about FRBs. Thank you.
So can we go back to the basic theoretical ideas on
But one thing that I think is lacking in this field is not one of the most glorious episodes in the history of scalar plasmas. As being well-defined out of an issue of mission calculations. Actually, just last week, Cerrone put out a quick calculation of the new mission from a relativistic shock, which is a nice calculation. And finds you get strong radio emission from relativistic shock at the upspeed medium as comparable energy density cold electrons and positrons and the magnetic field. And the efficiencies drops off rapidly as you move away from those cold conditions. So, putting this in a magnetar wind nebula context, I don't know how such efficiency arrives. But it's a nice calculation. And it is really constrained.
So you were saying that because your namesake and all of that, your license plate, is the one that's touted as the leading.
The thing that
And you just cast doubt on, or at least Whaley cast doubt on your behalf. So maybe you could say why you don't think magnetars.
Wait, does your license plate actually say magnetars?
Yeah,
anyway, more well, what we do know is that if you release a lot of energy in a small volume, that's the radio wave, that will produce radio waves. And that comes from all over and exploding black holes, which don't work in this context. The basic problem with magnetars as I see it is they're known to produce relativistic explosions, setting off maybe 10-kilometer sized plasmoids. But how, the problem is how do we convert dynamic state of that plasmoid on a 10-kilometer scale into centimeters? You do that efficiently without converting most of the energy back into the particle.
Doesn't that say, I mean, the other, I can read the press.
It could be alien.
Okay, well, maybe you will lead us in that direction. But the other one was coalescent objects, which would seem to have an even harder time with your
Yes, well, one of the big problems with any sort of compact object releasing this amount of radio waves in any sort of dynamic state, like colliding neutron stars, is that you have a lot of plasma around, and the very bright light radio emission will basically scatter off this plasma and close condense down below the disappear.
You do what?
Close condense.
Good word. What do you mean by that?
Scatter.
Stimulated scattering, okay.
You want to describe students with the forward and reverse channels of stimulated scattering cancel each other, but the recoil, which gives energy for a photon to the scattering electron, and the brightness temperature is large enough. Energy in the coherence of these photons all even up.
So far the press has not picked up on your
Good.
possible model, but you're saying that you can satisfy by the small scale some of the problems.
This dark matter is modeled as a fraction of those close to black holes.
But can it deal with a repeater like these things that are saying?
And I already all calculations and repetition.
So you think it's consistent with both things?
Well, there's not a data on the second repeater.
Okay, so should we quickly move on to others if they have questions?
Yes, I mean, this is going on too long about this.
But yeah, I think we have time for maybe a couple of more
But the
questions.
bottom line is that theoretical work that's being done on the mission processes and FRB's just solid theoretical work. And as I said, this beautiful paper last week that I finished people produced by Cerrone, which doesn't fill in that gap, but its astrophysical applications are, in my mind, questionable.
Okay. Yeah.
Are there efforts to correlate this measurement with gravitational waves observations?
To correlate fast radio bursts with gravitational waves.
Correlate with gravitational waves?
So there's been discussions between LIGO and CHIME about whether that would be interesting. I don't think anybody has found it interesting enough to do real-time work. Of course, after the fact, after they're published, anybody can go back and compare them. But there's been no agreement of doing it anything real-time. So,
What are your thoughts on the significance of the scintillation properties of the repeater versus the two repeater versus FRBs that we've observed so far compared to those that observed nocturnes? How do you read the significance of them? I know they're very different.
oh, I don't think there's a significance. I mean, based on a sample of 2, you can find for every one of these, there are probably another 5 of the regular ones that look very similar to the repeating ones. Not all of them do. And I think based on that statement, I mean, we know that they all show a broad range of both duration and frequency structure. And some of them, even some of them that have not been seen to repeat, look a lot like the ones that do repeat, and some of them look different. So I think at this stage, I think we just, anything can happen. I don't think there's any information based on a sample of 2.
It would be very nice to know how common frequency time structures and FRBs that don't repeat.
There are a couple of other ones. Molonglo's burst, for example, have. Indeed. And of course, that's one thing time will deliver. It will deliver a large number of bursts with good time and frequency structure, especially once we get the baseband analysis running. I believe Ryan is going to be the one leading much of that. That's not your main goal, but I think as a side product, you'll know the time structures of these things.
So when's the next paper?
I don't think there is a concrete time plan. I always think one should have one, but of course, it's work. There are tons of these things, yes.
Well, don't keep us in the dark too long.
Okay, if there are no further questions, let's thank Whaley.